All right, so we know that the force of gravity is given by two equally valid equations. It's equal to big G times the mass of the two objects that are being gravitationally attracted to each other, divided by the distance, the radius between them squared. And this works always. And it's also equal to the mass of an object near the surface of the Earth times g, or I guess the mass of an object near the surface of any planet times g for whatever that planet is. So this is fine on the surface of a planet. And when we, as we demonstrated in the previous video, the surface can be pretty broadly defined. And so if you are on top of a mountain, or you are in an airplane, or you are on a building, you are still on the surface of that planet. Because as far as the planet is concerned, like if I draw like a picture of the Earth, there's the Earth, right? And then if I add all the mountains and the buildings and everything, it still looks exactly like that because they are so small that you can't see them. And so although we think of things like mountains as being really tall and really amazing from the perspective of our equation, which only cares about how far away we are from the center of the Earth to the center of us, doesn't really matter if we go on top of a mountain. It's not really going to change anything because it's not even a noticeable change. However, in order for, we know this equation works, and so these do have to return the same value. And so we should be able to actually figure out what little g is for any given planet based on some other parameters. And so let's just check it for the Earth. We know what little g for the Earth should be. And then the other values, the mass of the Earth is 5.97 times 10 to the 24th kilograms. The way we actually figured this value out is by doing the opposite of what we're about to do. You can figure out, once you know what g is, you can figure out what, and you know like the mass of like a given object, you can figure out what the mass of your other object is. And so we actually use this equation to find the mass of the Earth historically, but we can also use that value that we now know is right to make sure the equation does what we want it to. Knowing that the mass of the Earth is 5.97 times 10 to the 24th, which is not something you need to memorize, is something that would be given to you if you ever needed to use it. G, I'll just write down so you have it, 6.67 times 10 to the negative, times 10 to the negative 11th kilogram, or Newton meter squared per kilogram squared. And the radius of the Earth, remember, depends on where you measure it from, but we're going to use that same value we were using before, which is close for at least most points on the Earth. 6.37 times 10 to the 6th meters. I would like you to, using this information, I would like you to solve for little g for the Earth, which of course we know should be 9.8, right? Should be 9.8 meters per second squared. And so I would like you to actually punch these numbers in and verify that that works out. So I will give you a moment to pause the video and go ahead and try to do that, and then you can unpause when you are ready to check your work. All right, so we can interpret this equation as if we were dealing with an object near the surface of the Earth, the force of gravity would be equal to, let me go to a new page. So the force of gravity would be big G times the mass of the object times the mass of the Earth, divided by how far apart their centers are. And so the radius of the Earth is pretty much going to tell you how far it is from the center of the Earth to the center of the object, because any object that we are putting near the Earth is not going to have a radius anywhere near the Earth. And so we can just use the radius of the Earth squared. And that's also got to give us the same value as our other equation, which is the mass of the object times g for the Earth. And so if these two equations are equal to each other, then if we just divide everything by the mass of the object, we get that g for the Earth, little g for the Earth, is equal to big G times the mass of the Earth divided by the radius of the Earth squared. Or, in turn, little g for any planet. If you want to know what the local surface acceleration due to gravity is on the planet for any planet in the universe, it's just equal to big G times whatever the mass of that planet is divided by that planet's radius squared. And so g for the Earth should be equal to big G, which is 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared times the mass of the Earth, which we said was 5.97 times 10 to the 24th kilograms. So we'll get a kilogram and a kilogram to cancel out there. And then we're going to divide by the radius of the Earth squared. We said that was 6.37 times 10 to the 6th meters. Of course, that gets squared. So we'll have our meters that get squared and our meters squared up here. And so if we crunch all this out, sure enough, we get G for the Earth comes out to about 9.8, which is the value that we use because it's the value that it is. And of course the unit, right here it's written as newtons per kilogram, but remember a newton is a kilogram meter per second squared, and so if we divide that by kilograms we get meters per second squared. And so sure enough, this does actually work. And again, you can use this for any planet. You don't just have to use it for the Earth. You can now figure out what the surface acceleration, free fall acceleration is on any planet. And historically, again, the way we actually figured out the mass of the Earth is by doing this backwards. We knew what the surface acceleration was because we could just drop things near the surface of the Earth. We were able to figure out the radius of the Earth because it's basically a big sphere, and so if you walk around on it and make careful measurements, you can figure out how big it is. G can be very carefully and very cleverly measured by putting some very, 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 very heavy objects near each other. I think historically like a big ball of lead and a pool of mercury were used, and you can notice just the slightest, tiniest increase in force between them. But that tells you you can use that to solve for what the force of gravity is when those objects got near each other, or what big G is when they got near each other. And then from there, the only thing left in the equation is the mass of the Earth. And so if we solve backwards, we get what the mass of the Earth is. And so that's where that number comes from. But we can also crunch forward through it to verify that we do, in fact, have the right number for the mass of the Earth.